Scholz star is a dim binary stellar system about 22 light-years from Earth. Around 70,000 years ago, this star system was an awful lot closer to us. This is the story of the star that nearly wiped out humanity. Spotting these stars is extremely difficult, and it wasn't discovered until 2013 by Ralph Dieter Scholz. When they later analysed its movement, they determined it appeared to be moving away from us. Using detailed data and our own movement, they were able to determine that this star passed within a mere 52,000 astronomical units from our Sun, some 70,000 years ago. The Scholz star system consists of two stars. Its primary star is a red dwarf, the second is suspected to be a brown dwarf. The total mass of this system is small at just 0.15 solar masses. The pair orbit each other at a distance of about 0.8 astronomical units, taking roughly 4 years to complete an orbit. In 2019, high-precision images helped to refine the calculations and put the closest point at 68,700 astronomical units around 80,000 years ago. What effect would this have had on our own solar system? Unfortunately, there are no human records that date back this far, but around 74,000 years ago the Earth underwent a catastrophe when the super-volcano Toba erupted. This event occurred at what is now Lake Toba. It was the last in a series of at least 4 caldera eruptions at this location, with the earliest known caldera having been formed 1.2 million years ago. The pyroclastic flow of this eruption destroyed an area of at least 20,000 square kilometers, with ash deposits as thick as 600 meters. It has been estimated that its volcanic explosivity index was at the highest rating on the scale. The eruption mass was at least 12 times greater compared to the more recent 1815 Mount Tambora eruption, which caused the 1816 year without a summer in the Northern Hemisphere. Some scientists have speculated that this could have caused a local cooling of 15 degrees for 3 years after the eruption, and that the cooling would last for decades, devastating life. A 10-year volcanic winter triggered by the eruption could have largely destroyed the food source of humans and caused a severe reduction in population size, creating a bottleneck in human evolution. Markers in the human DNA suggest a very low level of genetic variation in humans, which may indeed be caused by our current DNA being based on a very small number of survivors. In fact, so severe was this bottleneck that only around 10,000 individuals survived the rebuilding of the human race. This evidence was based on coalescence evidence of some genes and the relatively low level of genetic variations in humans. Subsequent research seems to show that the effect on the climate was much smaller than originally proposed, and that the observations of genetic evidence could be explained in a different manner. Nonetheless, is there any connection between these seemingly different events, the closest approach of a star and the subsequent flaring of a volcano? In the standard model, the approaching star could only disrupt the comets in the theoretical Oort cloud, which has never been observed and only hypothesized. A disturbed comet would take millions of years to fall towards the inner solar system, so from the mainstream perspective, there can be no connection between these two events. In the electric universe, we gain a different perspective on the scenario. There are a number of different aspects that are worth considering. First, we must take a little detour. When Voyager 1 and 2 flew past Jupiter and took images of Io for the first time, it appeared to be a satellite covered in volcanoes. To scientists' great surprise, they were not dormant but appeared to be active volcanoes. Detailed pictures of the plumes from one of these volcanoes were rather striking, in that the plume material was ejected in a well-defined cone whose geometry showed converging rather than diverging matter at large lateral distances from the vent, and concentrated in striations. We have a volcanic vent with an exit velocity of about 0.5 km per second, but with the volcanic effluent concentrated into a cone further tending to concentrate into filaments that terminate on a narrow, well-defined concentric annulus. In the late 1950s and 60s, Hannes Alfvén directed a program of research on the physics of the plasma gun. One of the things that inspired him to conduct this research was to try and understand the origins of the planets and satellites. Thomas Gold was the first person to suggest that the volcanoes might have an electric origin in his paper published in the Science Journal back in 1979. Nearly 10 years later, both Peratt and Dessler would combine their knowledge of plasma experiments an understanding of the Jovian system to come up with a radically different model of what might be causing and driving the eruptions. Plasma in Jupiter's magnetosphere injected from Io creates what is called an Io plasma torus. This flows past Io with a speed of 57 km per second. This, coupled with a magnetic field around Jupiter, means that the voltage induced across Io would therefore be around 400 kilovolts. They have also managed to observe approximately 10 to the power of 6 amps flowing out of Io. It would therefore seem plausible that the current would tend to concentrate in the volcanic plumes, which would give the current easy access to the highly conductive molten interior of Io. Peratt and Dessler proposed that the crust, consisting of sulfur and frozen sulfur dioxide, would be a relatively poor conductor, meaning that the current would be directed into the volcanic vents. If we assume that the available power is equally divided between the 4 largest volcanic plumes, we have about 10 to the power of 11 watts of continuous power available for each volcanic plume arc. This is roughly equal to the kinetic energy flux of the material issuing from the volcanic events. A small fraction of this power can account for the faint auroral glow reported by Cook in 1981. One question that is worth considering is why is the surface of Io covered in sulfur when all other Jovian moons are ice moons? If these electric discharges are occurring, then it is highly likely that the transmutation of elements is occurring. Io has the same icy nature beneath its surface sulfur. Water is dissociated into hydrogen and oxygen. The oxygen could be transmuted into sulfur. So, if we consider that any increase in electrical activity would likely find the weakest spot to equalize from, these are likely to be pre-existing volcanoes. So, could increased electrical activity in the solar system have triggered one of the largest volcanic eruptions, and can this be linked in any way to the passing of a star close to ours? With a star passing so close to our own, is it possible that the star could end up being captured? In the electric universe, capture is only likely if the plasma sheaths of each star, or the astrospheres, connect, and there is a difference in electrical potential between the two systems. Since the heliospheric boundary is of the order of 100 astronomical units, the reality is that their approach would have to be much closer for it to be considered a near miss. But that does not mean that it does not have a severe impact on both systems. In the electric universe, we assume that each star is the anode and the heliopause is a virtual cathode in a galactic Birkeland current filament. The vast volume of space in between the star and the heliopause is made up of infalling electrons drifting slowly towards the Sun in the small electric field of a dark mode plasma discharge focused on the Sun. The weak electric field also produces the solar wind of positive ions, still accelerating past the inner planets away from the Sun. Overall, the system has a net positive charge, constantly attracting new electrons from outside the heliopause. If another star system approaches our solar system, even at a significant distance from the edge of the heliopause, they will start to exert a repulsive force on each other. As the force will be equal and opposite for both systems, this could cause a small but significant change to the rotation of the Sun around what is called the barycenter as they end up being deflected away from each other. There is a possible link to the Sun's motion around the barycenter and many long-range changes on the Sun. This could be due to the alterations in the position of the incoming Birkeland current relative to the Sun. We know that the activity of the Sun seems to be linked to activity on other planets, so could a dramatic change trigger changes on the planets in the solar system? Another aspect to consider is the polarization of both star systems. If we consider that we have both free-moving positive ions and electrons within the heliopause, then as one star system approaches the other, at some point the distances between these two systems is close enough for the electrons in one system to become attracted towards the other star. If we also assume that it is difficult for the electrons to cross back over the virtual cathode, and if we consider that the electrons have less mass, this means that they are more readily moved. As our Sun has a greater mass compared to Scholz's system, is it likely that it therefore has a greater overall positive charge and is able to pull the electrons towards it? At the same time, this would create a net negative space charge at the front end of the Scholz star system, repelling electrons away from the Sun side and creating a net positive space charge. This rebalancing of the initial charges during the flyby would have a ripple effect throughout the solar system, impacting almost every planet either by causing an increased solar wind directed towards the Scholz star system or an increased electron flux on the other side. Could this lead to changes in the local currents flowing in and out of planets, leading to more electrical activity throughout the crust? What if the charge on the Sun was strong enough on the closest approach to rip electrons out of the Scholz system? Could this in turn trigger changes in the planetary current system on any planet that would be in the firing line of this? Or would it initiate short-term increased activity on the Sun, which as before might be linked to increased activity on the planets? There is much to consider in terms of the interaction of two star systems with each other and the ripple effect that this might have within each system.